Well, folks, this is Tom from anti-proton.com, and what I'm going to show you today is a little bit more interesting than what you see right here. This is me just being stupid. I have a CDV700, and I have its check source connected directly to a spectrometer. I was looking to see what was inside of the check source. Apparently, it's not very gamma emitting. But anyway, let's get rid of this, because this is neat and all, but it has really not too much to do with what we're dealing with today. And instead, let's do something more interesting. Let's calculate half-lives using a calculator. And you're like, wow, that's so interesting. No, it's not, because it's a calculator. Calculators are boring, meow. Well, that's not necessarily true, because we're going to do this with nuclear material. This right here is it's called an isotope generator. It should probably be called a radionuclide generator, but whatever. From Spectrum Techniques from Oak Ridge, Tennessee. It's not actually from the Oak Ridge National Laboratories, even though they are in the same area. It's from a company that's nearby there. And these guys produce piles of radioactive devices and things like that for people. They even produce stuff, I think, for the government, too. So let's open this up, see what's inside. Ta-da! We have a barium-137M generator. These little metal containers to put the material in. Planchets. I'm just going to call them metal containers because I hate the other word. And a plastic syringe. This plastic syringe is what you squeeze this stuff through. Now basically what it boils down to is you've got this little device right here, which is all capped off and everything right at this moment. It's been swipe tested and cleaned. And it has 10 microcuries of cesium-137. That's 370 kilobecquerels of cesium-137. And basically what you do is you connect the syringe and you squeeze some of this elution solution through it. Elution is the solution to dilution? Well, anyway, whatever. You squeeze this stuff through it right here, and what it does is it bleeds out a little bit of the barium-137M, and it leaves, hopefully, the cesium-137 behind. And then we get to study it because it has a short half-life of about 2.55 minutes, plus or minus. I'll throw all that up there in a minute. And basically it quickly decays and allows you to literally see a decay occurring. It's harder when you do stuff like rainwater decaying and stuff like that because there's multiple radionuclides that chain into one another. And I'm actually going to cover the Bateman equation today too, because I've said a couple times I was going to explain a little bit about that. And I'm not going to go into the humongous, massive, epic details of the Bateman equation because it's quite complex. But I'm going to do it for a parent-daughter-daughter scenario, the very simple, basic one, and show you how to compute it too. So let's figure all this stuff out. As you can see, the spectrometer is showing a nice peak right down here for cesium-137, and the Geiger counter responds to it, although not very well. That Geiger counter is not very sensitive. Let's use something a little more sensitive than that. This 1-inch sodium iodide scintillator, which goes hard over. Actually, let's convert that to times 1000 mode. So now we have 0, 100, 200, 300, 400, 500,000. So it goes up to 500,000 counts per minute, and we'll go over here and test this. Kind of trying to guess where the device is. And it looks like we're nearly at 200,000 counts per minute. We can get a lot higher than that if we put the unit a little bit closer, distance inverse square sort of taking effect. We're going to leave this on through the test because one always wants to have some kind of detector running. And we're going to test everything using the spectrometer here, which has something called multi-channel scaling mode. And it will basically it takes each one of the channels, the 1024 channels, and it will sit on a channel and count as many counts as it can receive for a period of time, then jump to the next one, then jump to the next one, then jump to the next one. So we should get a nice curve going all the way across. It's a little bit easier than trying to use a scintillator or something like that with just a little analog dial or even a Geiger counter. So we're only looking at gamma in that regard. So let's get the experiment started. Basically, I'm going to open this up, squeeze out a little bit of it, and put it in front of the actual device here. And we're going to watch it on the screen, and we're going to take a few measurements over a period of time. And then we're going to mathematically calculate what's going on. And then afterwards, I'll just show you the results of everything like that. So let's get going. All right. So I have gloves on right here. Check my gloves out. I'm wearing safety goggles too. I probably don't need them, but you know what? I'd rather have them on and not need them than not have them on and need them. With With something like this, because it's liquid, you should always wear gloves. Very, very important. By the way, there are many schools and universities that actually, oops, this thing's falling over, that actually use this actual barium generator. So it's typically considered safe by the scientific community. You can argue whether you think it's safe or not, obviously. Safe is sort of a relative term, right? Okay, so let's get this guy right here. Pop the cap off of it. And this will go right inside of here. So we'll just stick that in there in a minute. Let's get ourselves a planchette. And now we will squeeze a little bit of the elution solution. It's not much. Get a couple cc's, right? Get a good healthy dose of it. There we go. Into the actual device. And let's close everything up. Move this out of the way. And for that matter, we'll move this out of the way too. Alright. Now, let's affix this to the top. And then pull this little thing off here. Alrighty. And now we squeeze a few droplets out. Alright. Simple as that. Take this little guy. See, we've already spilled some on our container right here, but that's okay because it'll all decay away in a short time, leaving nothing behind. Now, we'll take our little piece of foam, put our piece of foam down right here. We will put this, oops, God, I'm going to drop it, my hands, right on top of it. We're going to move this away, and the reason is we don't want to affect anything. Alright, there it is, sitting right there. Now let's see whether or not there's anything coming out of this. It's obviously radioactive, but let's see how radioactive it is. About 120,000 counts per minute. And since we're actually using cesium-137, we can actually switch this thing to energy units and actually get a reasonable guesstimation of what kind of energy units we're saying here. Two milliroentgen per hour. I should have had this thing set to microsieverts, right? Oh well. At contact, we're getting 2 milliroentgen per hour. What's that, like 3 microsieverts? It's not much. Alright, so now we're ready for our test. There we go. And we'll put gloves on again before we actually touch anything here except a little foam, which is clean. So let's start the test and see what happens. Alright, and so here we are a little while later, and as we can see, this has gone back down to normal. We're not getting like anything off of it. I mean, basically nothing. Let's see what the scintillator thinks. The scintillator is a bit more qualified in this regard. Let's put this on slow mode. Okay, good. Scintillator's background is normal for me. It's about 2,200 counts per minute. Basically no change. Alright, Now, I'm not going to touch this for a little while anyway, just because I think it's a smart idea to dispose of it with gloves and everything like that anyway. Although this is basically now become just inert barium-137M. I wouldn't drink it or anything, but it's effectively harmless at this point. So let's go back and look at some of the numbers and put them into the calculator and see if we can actually figure out an equation that best describes how this decays. And by doing this, we can understand the concept of decays a little better. And then after that, I'll show you how to solve quickly something like a Bateman equation for when you have multiple parents and daughters and so on, as opposed to just something very simple like this. So let's go back and look at the numbers. All right, having gotten the data, we can now calculate the data using old-fashioned techniques. And I'll show you kind of how to do it on the new way too. So first off, we'll clear off our workspace and let's see here. Get out a piece of paper. We can write right on top of this paper. We'll need a ruler, maybe some protractor type things. And you're thinking to yourself, if you know anything about nuclear physics and decays and stuff, what the hell's he doing? Why isn't he just using this? It's a simple equation. Well, I just want to kind of show you this technique a little bit, then I'll show you like the fast, super modern way. So let's get started. Alright, so that was painful. I absolutely am terrible at drawing, as you can see. All I did was I scaled all the numbers and drew out a line right here. Basically put, I took counts that I got at a particular time and the time that they occurred. So as time went forward, counts went down. Very simple. Took the measurements, just scaled them out. Now that's the old-fashioned way of doing it. As you can see, it works perfectly fine, but let's do this the right way. Let's do this more effectively than what we just did. Now, here's how we can do that. We can use our calculator for that, and the reason to use the calculator is because calculators are awesome. Okay, what we can do is we can take, we already know that we have a decay equation, we already know that we have a exponential decay going on, right? It's pretty straightforward. You saw the shape of it. It was pretty much an e to the x type equation. So we know that these, well, let me get a piece of paper that's white to help out. Alright, so I got a white sheet of paper. So most of these types of equations are E, which is Euler's number. It's often mispronounced Euler's number because it looks like it's spelled Euler's number, but it's actually Euler's number. And you raise this to the negative decay constant. Now, don't you hate when people toss out these Greek-looking symbols right here? This little guy right here can be a bit of a problem if you don't know what it means. So let's figure out what that means. This, in this case, is equal to the natural logarithm of 2 divided by the half. There's an L in there, huh? Life. My writing is terrible. Absolutely hideous. So, do you see what I mean? That's that. So, e raised to the negative natural logarithm of 2 divided by the half-life. And it's kind of important to have a decent calculator for this, or be pretty good with basic math. You can actually use a something like this calculator right here, this little $10 calculator I got right here. And what you do is you find E, which is right there. You shift and hit E. And you raise it to, let's see, I haven't used this guy in a long time. Where's the negative symbol on this thing? There, negative. And then what you want to do is you want to put in the natural logarithm, that's this guy right here, of 2. Close that off. Lots and lots of parentheses to make sure everything stays the way you want it to be. Divided by the half-life. Now, And the half-life for the isotope we were dealing with right this moment was about 153 seconds. I'll show you, we can prove that in a minute. So let's say 153 seconds. Close that off, and we'll multiply it by some time. Let us say 153 seconds goes by. It's exact half-life. We should get 0.5. And we do. We get 1 over 2. The reason we get 1 over 2 is because these two guys matched up. We did this. Time. Time was the half-life, okay? So this causes a decay to occur, and you end up with this number being multiplied by like the activity of a sample or whatever you want to do it with. The way to figure out, if you can figure out this symbol right here, you're good, because you probably already know this. You probably know how long the experiment took. So here's how we can figure this out. Okay, now in order to understand the graph that we just went through, let's understand what's actually going on. First off, we have an unstable radionuclide. You shouldn't call it an isotope. You should call it a radionuclide, called cesium-137. It has a half-life of 30.1 years. That means that however much of it I have, in 30.1 years, there will be half of that much, and so on and so on and so on. Okay, now it's decaying down into this thing, guys, hurt your ears with that, called barium 137. Again, it's 137. It's a different number of protons, different number of neutrons. Total number of protons and neutrons is the same. Anyway, it's stable. Barium is stable. Like, you can put it on your desk and it would just sit there and be like, I'm barium. Look at me, I'm stable. So this decays to that. Now, 5.3% of the time, it just goes bloop, right down, and that's the end of it. It's instant, perfect, absolute, flawless, flawless. It goes right down to the bottom, and that's barium-137N. That's great. It's very simple. You don't need to do any amazing amount of math. Just kind of figure out how fast it's decaying. You're good to go. 94.7% of the time, that doesn't quite happen that way, though. That's a pretty good amount of the time. 94.7% of the time, it wants to jump down to barium, but it gets stuck about halfway. What happens is it becomes barium, but the nucleus is still extremely excited. It was not a very perfect thing. It's very perfect. I mean, very excited nucleus right here. This is called barium-137M. This little M right here means metastable. Is in a metastable isomer. That's what you actually call it, a metastable isomer. And so basically this means that this barium-137M is not really quite stable. It's kind of stable at an excited level. That's what metastable means. And it's quite statistically provable how long it will take for it to drop back down. In each individual one of these can decay down to the ground state instantaneously, or it could wait 20 years. But on average, statistically speaking, half of whatever you have of this will be gone in 2.551 minutes. And just kind of like this guy right here, it's the decay rate. So 94.7% of it drops to this unstable state right here. 14.9% of the time, the eventual decay will result in bloop, going straight to the ground again, no problem. However, 85.1% of the time, there is the emission of a gamma ray. Now, what happens? A gamma ray is a powerful high-energy photon is emitted with all this extra energy jammed into it, the energy that needs to go away and be like gone and pesky for this thing to calm down. It's kind of like letting out a big puff of steam at the end of a long day. Anyway, that puff of steam, if you like, that exasperated release, if you will, is 661.66 keV. That's 661.66 thousand electron volts per photon. Bam! That comes shooting out, and that allows the atom to decay. So these are the three different possible ways that it can decay. I believe off the top of my head there's a fourth extremely low probability emission that cesium-137 is capable of doing. I'd have to go look that up. I can't remember off the top of my head. But who cares? This is we're not doing our PhD right this second. We're just looking at this kind of simply. So this is cesium-137. Now, what we did when we took that generator, the generator is full of this stuff. Barium generator is full of cesium-137. You put that elution solution, I love saying elution solution, which is the solution to pollution. The elution solution squeezes out
barium-137M and barium-137. These are the two right here that are squeezed out. So you really have a lot of this stable stuff here, which isn't doing anything. It's just sitting there on the table like, you know, I'm barium-137M. Now, this stuff right up here, though, the M, that's what's decaying. That was the radioactive stuff we were seeing. That was what was shooting those gamma rays everywhere. And it was decay until it was completely down to the ground state and there wasn't any of it left. And it took 2.551 minutes for each half of that to disappear, right? So let's look at that equation. Let's look at that actual decay chart and see. So here's the decay. Now you probably think to yourself, this isn't exponential decay. That's sort of like linear looking. See how it looks like a line, aka linear? Well, that's true. Let's click the linear button because we're actually looking at this in a logarithmic view, which makes the logarithmic type stuff look kind of flat. So let's kind of click the linear button. Now we're truly seeing a real decay. See? Now these numbers, you know, the distance from here to 1,000, the distance from here to 2, and here is equal all the way up. It's nice and linear. Now when you make the world linear, all of a sudden you'll notice the decay equation looks logarithmic. Okay, so you saw me try to figure this out with a piece of paper. That's the incredibly boring way to do it. If you want to fall asleep, for example, you have trouble sleeping and you tried melatonin and it just didn't work for you. You tried drinking and that certainly knocked you out, but then you woke up with this terrible headache in the morning. So you think to yourself, how can I sleep? Well, I can use the paper and pencil way to solve logarithmic equations. You're completely asleep. Here's what I would recommend doing. Taking your exponential equation and picking 2 points. 2 points. Point number 1 and point number 2. I have no idea why I just selected those as ROIs, but whatever. Then you should select them as ROIs. Pick 2 points. In fact, you know what? Actually, I will do that ROI. That would be interesting. All right. Point. Okay, it won't do it. Damn, there. And let's grab another point right here. And there. See these 2 points I've selected? That over there. These 2 points, what we'll do is we'll figure out. Let me put a grid in here. Okay, so what we're going to do is we're going to call this right here the number of counts, and we're going to call this right here the time. Each one of these channels, if you recall, the spectrometer spent time in each one of these channels, 2 seconds apiece. So let's grab two values here. Now the ones I selected are not the ones I actually used for my example because I like to solve the equations before I do them. Otherwise I'll be stuck, you know, hitting some error I typed in and screwed up. Right? I got channel 52 and I got 5,188 counts, and down here I got channel 270 at 827 counts. Okay, so let's solve this right here, and this is pretty easy to solve. Let's get my calculator here. All right. So, do you remember this lambda symbol right here? The lambda symbol was the decay constant in a decay equation. I'm sure I've shown you this before. So this right here is a little chunk of math that tells a calculator or a person doing the math or whatever just how often something decays. And we can figure it out pretty quickly by taking the natural logarithm of 2. Let me get my calculator. Here we go. Let's move the calculator over. Here's my Ti-89 titanium, a nice little picture of it. And I can figure this value out. This is kind of an important value to figure out by taking the natural logarithm of 2 and dividing it by the half-life. Now, the half-life of barium-137M was, what was it, 2.551 minutes. It works out to 153 seconds, all right? So all I have to do is I take the natural logarithm of 2. Now let's see, where's the natural logarithm in this thing? I can't recall. I use it all the time. And like, I can always do it when I'm trying to find it, but when I'm actually using it. But you know, the hell is it? I mean, literally, I use this all the freaking time. Where's my natural logarithm? Okay. So you take the natural logarithm of 2. I actually realized that if I took my fingers and just touched the screen as though with the calculator, my muscle memory would tell me where it was. And sure enough, it did. So you hit the second button. And then you hit the X button, which is the ln. If this is actually kind of a blue color, if you look, see, natural logarithm. So second, natural logarithm. And then you type in the number 2 and hit enter, and that's the natural logarithm of 2. Then you click the divide button, and then you type in the half-life, 153 seconds, and you hit enter. And then that gives you a number, like negative 0.00 or something or other. That will be the decay constant. So let's zoom this out just a little bit. See, like that. That's how you do it. Boom. Natural logarithm of 2 divided by the half-life. Natural logarithm of 2 divided by the half-life. That's decay constant. Natural logarithm of 2 divided by the half-life. All right, so let's step this back a little bit. And here's the equation we can use to figure out what's going on in this whole graph. If we take the natural logarithm of 2, yes, you're going to have to really memorize this because it comes up all the freaking time. Natural logarithm of 2, and you divide that by this thing, you'll end up with hopefully 153 seconds. So you end up with a half-life. So we'll take data point 1, which is going to be a particular time, maybe like a couple hundred seconds into the test, and then we're going to take x, which is going to be the number of counts we got for that. So this is one chunk of data, a time and a count. Time, count, right? And then we're going to go over here, you're going to do the same thing again, but this time we're going to have a second time, like a little bit later on in the decay equation, and we're going to get a second count. So like maybe 10 minutes later or something, the count, the time. And we're going to take the natural logarithm of these two numbers, subtract them from one another, and then divide that by the times subtracted from one another. So let's actually do that. All right, so let's see what I chose. I chose 56 seconds into the test, very early on, when I had 6,367 counts. And then I also chose 558 seconds, that's nearly 10 minutes, when I had much less, 720 counts. So what did I do? Took the natural logarithm, second to, well, sorry, I took the natural logarithm of this number right here. So second natural logarithm, 6,367, enter, and then I subtracted that from this number, divided it into this minus this, and I divided natural logarithm of 2 of the whole entire thing, and I came up with, now I have a negative, there shouldn't be a negative, I was kind of a fool, I was a foolish fool. The negative should have been right here, because when you're doing half-lives, you end up with a negative. You'll see later on. Just ignore the negative right this moment. It doesn't matter. See how my mouse covers it up? You can't even see it. There you go. I ended up with 159.6415 seconds of half-life. That is pretty darn close to 163. So we see that my method right here, it's not even my method, like, brilliant scientist years ago came up with this. I didn't do it. But this method is pretty darn accurate, right? It's not absolutely accurate, but it's pretty accurate. We came within 6 seconds of guessing the half-life using this method. The reason it's off is because the background is kind of interfering with the equation. If you wanted to be smart about it, if I wanted to be smart, I would have subtracted the background from every single one of my counts. I didn't do that because I was being dumb about it. The opposite of smart about it. Okay, so that's how we figured that out. Now let's take these numbers and see if we can do a little bit of quick math with it. This quick math should make life easier. We're going to use the calculator and the natural logarithm of 2 and that sort of thing. We're gonna calculate this. So let's move over here. Now the program I use from Texas Instruments that lets me capture what's on my graphing calculator makes these little freaking thumbnails. Look at this thing. Like, this is smaller than an iPhone, and an iPhone in itself requires, like, special corrective goggles just to even see. That's why I bought a Samsung Note, because I actually want to be able to see my phone. So anyway, ooh, just attack the iPhone. Immediately 1,000 subscribers leave, and I get like my video like commented down by a bunch of Macintosh fanboys. So let's figure this out. Let's kind of like do the math here with the calculator. We take 2.551, 2.552, whatever. If you go to multiple scientific quote authorities in this situation, you'll end up with various numbers for this. NewDat's probably one of the better places to go. Oak Ridge has a pretty good listing of it too. So you take the number, the half-life here, and you figure the half-life out with 2.552 times 1 minute, right? Because we know that it has a half-life of 2.552 minutes. So we multiply that by a minute, and we end up with 153 seconds, 153.12 seconds if you want to be specific. So now we know the total number of seconds. We just stuck with seconds to begin with. We didn't even have to do that equation. Now, we divide the natural logarithm of 2 into the half-life. Hum-de-dum-dum. Does that remind you of anything? Reminds me of this right here. So anyway, we do that, and we end up with the half-life. By the way, this is what the half-life actually looks like. See how it's .0, it's 0.004527. Okay, so that is now the half-life. We have this half-life as a value here, and you know how the calculator works. If you were to hit like multiply button and then like a 1 or something, it would say answer or multiply. If you start begin like another function, it'll just automatically drop the answer down. It'll say answer if you've seen a calculator before. So what we're going to do is we're going to hit the store button. I always call it the stow button. I don't know where it's the store button, you know, but whatever. So you hit the store button, and you're going to want to put that in a variable. And you could just take, you could hit the alpha for, you know, numbers and letters, and you could just give it any one of these letters like X or something if you wanted to. But I figured it'd be kind of nifty to actually use the real lambda function. So what I did was I clicked the store button, then I clicked the, is it the second button? I can't tell with the colors, so let me look at my calculator. Yep. Yeah, I clicked the second button, and I clicked the character button. Let me show you. When you do that, you get this set of characters, various possible characters you can select. And you go down here and you find this lambda. Like I said, you could make it X if you wanted to, but that's lame. Don't be lame. Be better than lame. And you hit enter, and you'll end up with, see the little answer thing here? You'll end up with this. You'll end up with the answer that we just got stored to the lambda. See how useful that is? Now you can do all kinds of math without having to type this ugly business in right here every single freaking time. So let's figure it out. All right, let's say that we have 1,000 becquerels of barium-137M, right? 1,000 becquerels, well, it's not really becquerels of barium-137M. This is not decaying. It's de-exciting. So we'll say that we have 1,000 atoms of barium-137M, 1,000 little 137M atoms. Somehow we actually know that, somehow. Then all we have to do to figure out how much is left over, because remember, this math is going to spit out a ratio, like 1/2 or 1/4, so we just multiply that 1,000 by the math. We take E, which is Euler's number, sometimes erroneously called Euler's number, because it looks like it does, for the record, look like it should be pronounced Euler's, but it is Euler's number, just kind of trust me in this. So you take that 1,000, you multiply it, so we do 1,000, and we do multiply by. Now we need to raise it to E, so we hit the little diamond button, and you see the E to the X, hit that. That's going to produce E to the X, right? Except instead of an X, what we're going to do is we're going to hit the negative button, and the negative button is, where's my negative button? See the negative button? Use the negative button, and the reason you want to do the negative is because we're doing decay, not growth. If this is like a business math class and we're like calculating growth of something, you know, or if you had like the growth of bacteria or something like that, then you want to, you know, get rid of this negative sign, but that's a little bit more complicated. And you want to just type in the lambda, and you want to multiply it by time. 600 seconds, that's 10 minutes. So how much does this thing change in 10 minutes? The result is that we have 66.1326 little stupid atoms of barium-137M left. That's it. Do you see how simple that was? But wait, there's more. If you were to take this 600 and change it to an X, then you could graph the whole thing, right? Well, you could do that. So you just use the F1 key and then do a copy paste, and you can go to the Y equals. Remember Y equals right here? You just hit that little button, hit the Y equals, and you can actually enter this equation into the graphing calculator, because it is a graphing calculator. Switch that 600 seconds to a T, and then graph it. Hit the graph button. Boom, there you go. And you can follow the decay equation all the way across and see at any given time. You could even do things like integrate it all the way across, integrate it from point here to know how many photons were emitted, that sort of thing. Very useful information, I think. Very, very useful information. All right. Now, I said I was going to do something else for you guys and show you a quick Bateman equation. The reason I'm going to show you a Bateman equation is because not everything decays in a simple sort of fashion. Yes, lots of things do. Not everything goes from a parent directly to a ground. See, like the barium we were working with was going from the parent, which is barium-137M, straight to the ground. Very simple. If you know how much barium-137M you're starting with, all you have to do is raise E to the negative lambda for this times time, and you end up with what's left over. Well, what do you do when you have a parent that's radioactive, which is decaying, and it's decaying into a daughter that's radioactive, that's decaying, and you're going down here to the bottom? How are you going to figure that one out? You'll use the Bateman equation. All right, so you have a parent. And let's just kind of go back for a second to cesium-137 and kind of look at that. You have a parent. You can figure out how much of it's gone in, let's say, 1 hour, 3,600 seconds. You can figure that out. All you have to do is take E raised to the negative lambda 30 times 3600, lambda being the decay constant for this, you know how much is left over, right? You can figure out how much of it is down here in the stable amount too, in the same sort of way. You know that this has a pretty short half-life, so you can kind of figure it out. The question you're going to really have to figure out is this, though. If you want to figure out how much total amount is left over, you're going to have to kind of know how much you have here at any given point. And another important thing is to figure out in general how much you do have right here, because you might actually not care so much about these guys. You might care about this guy right here. So how do you figure out how much activity you have into this? Well, there's a problem. On the one side of it, this is gaining radioactivity because this is losing it. And at the same time, this is spilling out into here. So basically, you have a big bucket of water that's pouring into here, and this is pouring water out into here. So how much water do you have in this at any given time? So we can figure that out pretty quickly, and we're going to do that with the Bateman equations. Let's go look at the Bateman equation. All right, so the Bateman equation is one of those equations that's not really actually that difficult to figure out. But you do have to apply yourself just a little bit. So here's the Bateman equation, and this is only one of them. Bateman equations are not like one equation. There's actually a bunch of them. It's sort of not so much of an equation as a style of equation, a methodology for doing something. This is a very simple one right here. Oftentimes you'll see this very simple one portrayed with typically another little bit tacked on over here for the initial starting amount and some other things, but we're not going to worry about that right now. We're going to say that we have the perfect ability to start with an exact amount of everything and blah, blah, blah. So, step one, figure out the decay constant for the parent. Remember how to do it? We already did it. Natural logarithm of 2 divided by whatever we're working with. In this case, we're dealing with cesium-137. So 30.1 years is 9,480,600 seconds. It's a whole bunch of seconds. So you take natural logarithm of 2 divided by that, and you end up with the decay constant. It's this incredibly small number, right? Times 10 to the negative 10th. Oh my God. You do the same thing for the daughter. That's barium-137M. And as you can see, natural logarithm of 2 divided by the half-life, 153 seconds, much less than this. You end up with this much larger number. It's still small, but much larger number. Okay, so this right here, for this whole big bit of Greek-looking symbols and stuff, with the subscript D to equal daughter, blah, 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 you just throw this out and replace it with that number right there. Throw this out, replace it with this number right here. Throw this out, replace it with this number here. All right, E gets raised to negative lambda. This is exactly the same equation we did a few moments ago, except the decay constant would be nothing more than this guy right here with a negative in the front of it. The decay constant would be nothing more than this guy here with a negative in front of it. Very simple, right? Subtract it. So let's put some numbers to this and see what we come up with. Barium-137M's decay constant, again, twice. Subtract it, raise it here. You just kind of follow this across, and this is going to produce the output of how many atoms, if you like, are available for the daughter that's in the middle. So here it is. You can enter that into the calculator like so. Oh my God, look how crazy that looks. Well, it does. I'm sorry. I used too many parentheses. The reason I use the parentheses is because sometimes calculators and other computers, in fact this happens a lot in programming languages, they tend to use their own order of precedence and execution and so on for deciding what should be done first. So lots and lots and lots of parentheses ensures that things always work the way you want them to. Make sure you don't accidentally override any rules of mathematics while doing it, however. Alright, so basically you type all this into the calculator. Now I'm going to probably put all of this into the actual details. You can just go harvest it and copy paste and all that kind of stuff, because you know that's always fun. And you see right here that within even a full 1 hour of running, and almost immediately in fact, that middle daughter, let's go look back at the middle daughter for a second. And the middle child. As you can see, the middle child right here almost immediately goes into an equilibrium with this guy right here. So this one's decaying, 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 and this guy's just staying right about at the same activity as this guy right here, right? This guy right here will appear to be at the same activity as this. That's why a lot of times people will take a cesium-137 sample and they say, I've got 1,000 becquerels of cesium-137. How many photons does that emit? I'll just multiply that by 0.851, 85.1%, and I'll know how many photons. And for the record, it pretty much comes out right. And the reason is because even though this intermediate step exists and all this other sort of stuff, it is effectively trivial in this form of equilibrium. So you will hold it this incredibly close to one, incredibly close to the parent's activity for, well, a really long time actually. Eventually, after a really long time, 100, 200 years, this will start to change. Actually, longer than that, I think. So let's throw this through the calculator now and kind of see what we come up with. Throwing through calculator, throwing through. Okay, here we go. Now, oops, let's pull up our calculator too. Calculator, where is the calculator? Here it is. All right. I love these little postage stamps. Thank you, Texas Instruments. For my example here, I used not yttrium. I did use yttrium, but I used strontium-90. Strontium-90, that's that nasty bone seeker radionuclide that's also often found in nuclear disasters after, like, Chernobyl and that sort of thing. It has a half-life of 28.9 years, right? You multiply that by 365 days in a year, by 24 hours in a day, by 3,600 seconds in an hour, and you end up with this big old number right here. This is how many seconds exist for the half-life of strontium-90. And you can get its decay constant by, what do we do every other time? You just multiply natural logarithm of 2 by the decay constant, boom, you got the answer. Strontium-90 decays to yttrium-90. Yttrium-90 decays to zircon-90. And strontium-90 begot yttrium-90, and yttrium-90 begot zircon-90. It sort of sounds like that, doesn't it? So once you get the answer, you can store that to P for parent if you like. It's up to you how you want to do it, but it's just for my example. So you just click the little store button, alpha button, and the P button. Where's the P button? P button happens to also be the store button. Make sure you hit alpha or that will do something weird. Okay, so once that happens, you can now calculate for the daughter. The first daughter, the middle daughter, which is yttrium-90, that has a 64-hour half-life, much shorter. So you end up in something called a secular equilibrium. So anyway, basically you take that 64 hours and you multiply that by 3,600 seconds. It's to figure out how many seconds there are in its half-life, right? And if I didn't start off with like 64 hours as half-life, if I started out with the more scientifically appropriate seconds to begin with, we wouldn't have to do this math. But that'd be my fault, right? So anyway, you take the answer to that. It's natural logarithm of 2 divided by that. I mean, it's sort of constant if you've noticed. Then you store that into D for daughter. I chose D for daughter. You could use A, B, X, Y, whatever you want. So there they are. And now you have two variables. You have P and you have D. And both of these two variables are showing you decay constants, just like you did with the cesium-137. All right. Next one, we put in this humongous thing. And by the way, if you want me to, I can show you sometime how to actually enter this into your calculator and save it as a function. You could call it like decay or something like that, and then you would just feed it the two variables, and you would never have to type all this ever again. Thank God for the TI-89 titanium. And yes, I'm sure they have an app for that, but whatever. I like the TI-89 titanium. So you know what? And there you go. No, Texas Instruments did not pay me to say this. If they did, they should have given me better stuff to show. I'm going to take 1,000 becquerels, 1,000 decays per second of strontium-90 to start with. There it is. Toss it into the rest of the equation, just like we've seen before, the whole equation. And I'm going to put it in for exactly 1 hour. I like using 1 hour, 3,600 seconds. And I come up with 999.951 atoms of becquerels of yttrium-90. That's how much yttrium-90. It's the middle radionuclide. That's how much would be there after 1 hour. Using that number and the other decay, and of course its actual decay scheme, you could then figure out how much actual activity would be, or how much of the actual daughter would exist, zircon-90. All right, so you can take this, copy it, take this, paste it up here into the diamond, hit F1 here, into the tracing function, and then you can just graph that sucker. See how it goes into equilibrium? Nice, huh? And so pretty much that's that. Now I'm sorry if Batemans are a little confusing. I didn't mean to make them confusing, but they are sort of confusing. If you have any questions, let me know, and I'll be happy to try to explain them. Hopefully I'm back, so that would be nice since I've been away for so long. But this has been Tom from anti-proton.com, and in the details I'll have links to the images in here so you can actually just go look at them if you want to. And if you see that I've done something wrong, please say something about it as opposed to just fussing like most people do. But thank you for watching my video.